All right, today we're going to look at one more individual gas law, because this week we're going to take chapter 11 into its final stages, and that means we need to add one more variable. So today we're going to look at Avogadro's law. Now, you guys remember Avogadro, and right at the very beginning of the year, we started off with something called Avogadro's number, which is this big number, 6.02 times 10 to the 23rd. That's definitely attributable to Avogadro, but that's not what we're going to be looking at here yet today. This is, on the face of it, seemingly unrelated. Here we go. This is what we call Avogadro's law. All right, as far as we are concerned, Avogadro's law looks like this. It says that volume is proportional to the number of moles of gas. We want to make sure that we specify that this is a direct proportion, meaning that as we increase the number of moles, the volume also increases. We see that here. And this is a simulation that we've been using for quite a while. Notice that the volume is at 2.75 liters. And I have it set so that the volume is not locked. And look what happens when we add another chunk of gas. Every time we add gas to this, the volume goes up, and it seems to go up proportionately by about the same amount every time, about 90 liters. And fairly interesting that as we are adding gas to this, the number of moles of gas increases, and also the volume increases. We're going to represent this law a little differently. And we're not going to be using calculations like this quite so much, but I'll show you what I'm talking about. It's going to look very similar to both Charles' law, which, as you recall, is the law between volume and temperature, V1 over T1 equals V2 over T2, and G and L's law, which is the relationship between pressure and temperature, P1 over T1 equals P2 over T2. Avogadro's law is going to look very similar, but we're going to take this Avogadro, I can't write and talk at the same time, Avogadro, and we are going to take this into a different direction. It's going to look like this, V1 over N1 equals V2 over N2. We'll get back to that in a little bit. What we want from Avogadro's law is this sentence. Equal volumes at the same temperature and pressure contain equal numbers of moles of gas. What this is referring to is any gas. It doesn't matter which one it is. And this is the part of Avogadro's law that we want to take home with us. Okay, this is the important part. Remember that up here it says, equal volumes at the same temperature and pressure contain equal numbers of moles of gas. And that means any gas. So equal volumes of any gas at the same temperature and pressure contain equal numbers of moles of any gas. Here's how we're going to interpret that. At standard temperature and pressure, what we know to be STP, 1 mole. And notice that it doesn't specify a particular gas. It just says a gas. That means any gas. Occupies a volume of 22.4 liters, which is called its molar volume. Let's make sure we set that. At STP, 1 mole equals 22.4 liters, what we call molar volume. Let's make sure we get that solid. At STP, 1 mole of any gas equals 22.4 liters. How are we going to use this? So let's take a look at a couple of examples of a problem that I might throw at you. So let me get you an example here. So Let's check this out. It says at STP, what volume does 3 moles of a gas occupy? Remember that we know that at STP, 1 mole of any gas is 22.4 liters. So in a question like this, would be saying how many liters would be the equivalent of 3 moles of any gas? It doesn't matter. And we're at STP, so we know that at STP, 1 mole of whatever gas we're talking about would be 22.4 liters. Make sure you have a calculator handy. I have this one. And so we're going to say, get rid of this, and let's put this over here so that I can see my calculations. We're going to say 3 times 22.4, and we divide by 1, which we don't have to do. And what's our volume? 67.2 liters. And that's the beginning. But we're going to take this a couple steps farther. For example, what if I was going to ask you a question that was not at STP? Let me give you an example of what I'm talking about. Okay, this question asks how many moles of oxygen gas are in a half-liter vessel, 0.5 liters, at 25 degrees Celsius. So the first thing that we're going to do is we'll calculate how many moles we have. We'll calculate what our volume would be at STP, because we can't compare volume to moles unless we're at standard temperature and pressure. So the first thing I'm going to do is say, okay, well, what would our volume be at STP? Because obviously as we increase temperature, we also increase the volume. So this is going to be a Charles law problem, and I'm going to say V1 over T1 equals V2 over T2. And our V1 is, of course, at 25 degrees Celsius, 0.5 liters. 25 degrees Celsius is our T1, but this is going to be in kelvins, 298. We're trying to find V2 at our new temperature, which would be STP, 273 kelvins. We expect the volume to decrease. So, busting out my calculator, we're going to cross multiply. I'm going to take 0.5 liters times 273, and then we'll divide by 298, and we know that our units cancel, so this is going to be our new volume, 0.458. Let's call that 0.46 liters. Now that we are at STP, we can find moles, and so we'll add one more step. How many moles of O2 are the equivalent of 0.46 liters? Because we're at STP, now we can say 22.4 liters is the equivalent of 1 mole of oxygen gas. And so we'll say on our calculator, 0.46 divided by 22.4, well, times 1, and then divided by 22.4. And this should tell us how many moles we have. And that is 0.02 moles. Now I can be nasty and ask you to tell me how many molecules that is, or how many grams that is. But we're going to take this one step further, and it's going to get nasty enough as it is. So welcome to something called gas stoichiometry. Let me show you what I'm talking about. Oh no! Stoichiometry! Oh no! We hate this word, don't we? Here's how we're going to use this. Here is a compound called calcium carbonate. It's a solid, but if we heat it, this little delta sign, meaning heat, then we get carbon dioxide and something called calcium oxide. Calcium oxide is also a solid, but carbon dioxide is a gas. So here's the type of question you can expect me to ask, a question like this. So here's the kind of question you can, here's the type of question you could expect me to ask about something like this. What volume of CO2 could be produced from the decomposition of 500 grams of calcium carbonate, and it specifies at STP? Will I ever make you do it at a situation where the temperature or pressure are not at STP? Maybe. Who knows? At any rate, let's try this one. So let's set this up like we always do. How many liters of CO2, that's our unknown, could we expect from 500 grams of CaCO3? Well, we're at STP, so we know molar volume is 22.4 liters per mole, and that means we need to find out what is the ratio of moles of CaCO3 to CO2. According to our balanced equation, everything is 1-to-1, so that makes it fairly straightforward. Let's get our CaCO3 into moles, and that means that we're going to need molar mass. And calcium being 40 grams, carbon being 12, and oxygen being 48 is exactly 100 grams. So 100 grams of CaCO3 in 1 mole of CaCO3. We know the ratio of moles of CaCO3 to moles of CO2 is 1-to-1. From our balanced equation. And finally, because we are at STP, we can say 1 mole of CO2 would be equivalent to 22.4 liters of CO2. So here's this whole big setup. Obviously, grams cancels, moles of CaCO3 cancels, moles of CO2 cancels. Should leave our answer in liters. So I'm going to say 500 divided by 100 times 1 divided by 1 times 22.4. What is our volume that we could expect? I get 112 liters CO2. And that is gas stoichiometry. All right, take that for a spin. And be aware that at some point, I'm going to ask you to do one of these at STP. At a situation that is not STP, but you know how to do that because just like we did up here, just find what your volume would be at STP, and then you can switch to a new volume at a different temperature, vice versa. Okay? Take it for a spin. I'll see you guys on the next one.